Hey everybody, welcome back. And we're gonna today, if you remember, you've got some homework due if you didn't turn it in yesterday. So please be sure to do that, and you can do that even right now with Mrs. Myers. And we've got a quiz that we're going to run here for the first 20 minutes or so of class. And following that, then we're going to jump into kind of our last topic in chapter 1, which is infinite limits. If you look ahead to the schedule that we passed out yesterday, next week we've got 2 lectures. I'll be here. But we have 2 more lectures, one on finishing up section 1.5 on infinite limits. One of them is a preview to what's coming in the next chapter, chapter 2, which is derivatives. Wednesday, just remember that I think you guys have community service that day, so all of your classes get smashed up in the morning again. So that's the 25th. And then Thursday, we have a review for our next exam, and that exam is going to be on chapter 1, which is all about limits and continuity, which is what we've been talking about. So we'll get to that. It's coming in a little while. We'll do a review for it. We should be good. We'll answer homework questions, that kind of thing. Okay, but for now, we're gonna pause and we're gonna take our quiz. Before we do that, let's pray, and then we'll pause the video here, take the quiz, see if there are any questions, and then following that, we'll move forward with infinite limits. So, Father, again, we just bow before you and acknowledge that you are good and mighty and awesome, and we love you, and we praise you, and we're so grateful to be called by your name and to be known by you. Thank you that you're here in this room in the midst of everybody here. Pray for all these students that you'd calm their nerves again and bring back to mind the things that they studied. Help them to understand well and express themselves clearly as they take this quiz. May it be an offering and an act of worship even to you, Lord. We love you and thank you for all that you've given us. In Jesus' name, amen. Okay, so go ahead and pause this and go ahead and take the quiz. And then in about 20 minutes or so, we'll come back and we'll get going on infinite limits. Okay, so you guys did the quiz. Hopefully not too crazy. So I'll try to grade those this weekend and get those back to you on Monday. In order to do infinite limits, in order to talk about infinite limits, I want us just to review real quick again, what's our kind of MO, what do we do when we're asked to evaluate limits algebraically? So the first thing that we do, so to do limits algebraically, first thing we do is always, that's right, plug in. So we try to plug in. There's lots of situations where that's going to work great. When we have continuous functions, it works awesome. But there are a lot of situations where it doesn't work well. So if I have a function that's a fraction and the top and bottom are both going to 0, the 4 things that I do, I may factor and cancel. I may do, if I see a square root, then I'm going to do conjugates. Okay, so hopefully you remembered that on the quiz. If you see fractions, you may get a common denominator or otherwise simplify in some way. Okay. We had the squeeze theorem, and when do I use the squeeze theorem? That's when you see the sine of something crazy or the cosine of something crazy that's like oscillating or doing something weird. There actually is another thing that we added to this list, but I didn't really officially add it on the list itself. If you have a piecewise function or an absolute value, we've kind of been doing this when we talked about continuity. If you have to take a limit and you've got different functions on the 2 different sides, do you remember what we do? We take a limit from one side and we take a limit from the other side and we see if they match up or not, okay? So if you have a piecewise function or an absolute value, look at the limit from the right and the limit from the left and see if they match up. Because that allows you to sort of break the problem apart and see what's going on the left side, what's going on the right side, what's happening overall. Okay? So that's kind of our, that's kind of what we've gone through so far. So the next, the question now that we want to ask is, what do we do if we have a fraction and the top doesn't go to 0 and the bottom does? Okay, when we take a limit. What do we do in that case? So let's look at an example. This is just an example, but it's going to give us some intuition as to what's going on. And then we'll create some definitions and we'll try to quantify some of these things. So so let's use the example limit as x goes to 0 of 1 over x squared. Let's look at the 1 over x squared function. Okay, I'm picking a function that you do know what it looks like. This is the volcano, right? This looks like a volcano. It looks like this. All right. So when x goes to 0, visually we can see this is not going to have a limit. What kind of discontinuity is this? It is an infinite discontinuity. Good. What I want you to see here is when I try to plug in 0, the top goes to 1 because it's just 1, but the bottom goes to 0. Okay. What ends up happening, I want you to think about this, just think about it numerically just for a second. If I were to take, I want you to maybe take out your calculator and think about what would happen if you plugged in, so if we were doing this numerically and x was going to 0, from either side we would maybe put in negative 0.1, 0.001, sorry, 0.01, 0.001, and then if we're coming from the positive side, we put in 0.1, 0.01, 0.001. Just try plugging one of those in to your calculator for a second. Just take a second, get your calculator out, try taking 1 over that number squared and see what you get. Okay, just take a second and do that. What you should see is that you should get a super huge number. I think you should actually get 1 million. Okay, and if you make the number on the bottom smaller, the overall number that you get is actually bigger. So a concept that's very important in understanding what's happening here is if I divide by a really small number, the result, and the top is kind of stays consistent, the result is a really big number. When you divide by, you've kind of seen this in reverse. When you divide by a big number, the result is a small number, but the reverse actually works too. So if you divide by a small number, you get a really big number. As long as that top is staying a consistent non-zero number like 1 or 6 or something like that. If the top and the bottom are getting small, then all bets are off. But if the top is approaching a specific non-zero number and the bottom is going to 0, what ends up happening is in all of those cases, you get a really huge number. Now, it might be a really huge positive number, like it is in this case, because the bottom is squared, or it may be a really huge negative number, or it may depend on what side you're coming from, okay? Yeah. So what we need to do is I want to actually give, when a function does this, I want to give this a name so that we can kind of talk about it. So let's throw a definition in here now. Okay, what we're going to do, the notation that we're going to use here is we're going to say the limit as x approaches a number of the function is positive infinity, or just infinity. Okay, when I write that, what that means, that if I'm approaching the number, in this case I'm approaching 0, but if I'm approaching from either side, eventually the number gets bigger than the function gets bigger than any cutoff that I can set. Okay, it means that eventually f gets bigger than any cutoff as x gets close to a. And again, we have kind of our two caveats from both sides. And it doesn't matter what's happening at the point. Okay, that's still true when we're talking about a limit. We're coming from both sides, but the idea is eventually the function is completely bigger than any cutoff that so if I cut this off at 1,000,000, eventually the function's completely bigger than that. Okay, the book uses the term unbounded. I don't like that term because it actually has a different meaning technically. So we won't say unbounded, we'll say infinite. But we're going to say that the limit as x goes to this point is positive infinity. Now, one huge note that I need to make here when I write this, okay, when I write this, this does not mean that the limit exists. In fact, if this is going on, the limit doesn't exist, right? That's something we've talked about before. This thing is not approaching a number. Positive infinity is not a number. Okay, so if I write the limit as x goes to a of this function is positive infinity, that does not mean that the limit exists. It just means the function keeps getting bigger and bigger and bigger, gets bigger than any cutoff as I try to get close to a particular number. Sorry, there's a train going by if you can hear that. Okay, so that's what it means if the limit is positive infinity. That's sort of a conceptual understanding. What about if the limit is negative infinity? Okay, what does that mean? Okay, it should have, the picture that you should, like if this is A, the picture that you should have in your head is something like this, right? And we'll talk about what this means graphically. I'll give you some examples graphically. But this means eventually the function gets smaller than any cutoff. Smaller means more negative. So the only difference here is that the function is getting smaller than any cutoff as x goes to a. It becomes more and more and more negative as x approaches a. Now, again, both sides, x, we don't care about what happens when x equals a. And again, this does not mean that the limit exists. Okay? So let's take a look. So this is what we're going to call an infinite limit. It doesn't mean the limit exists. It's just we're going to call this an infinite limit. So let's look at a couple of examples graphically. We've already seen a couple, but let's look at a couple of examples graphically. We'll talk about this a little bit numerically. And then we'll talk about how to do this algebraically. Okay, so graphically, let me just give you a graph here for instance. Okay. So let's have a function that does this, this, you may want to take a second. If you want to take a second and copy this, that's fine. Okay, so I'll just give you a minute here. Okay. Finished. Okay, so let's ask, what's happening as x approaches 1? What's the limit of this function as x goes to 1? Notice everything is getting bigger and bigger and bigger. So we're going to call this limit positive infinity. Again, if I said, does the limit exist at 1? You would say no. So technically, it's also correct to answer this dne. But if you say positive infinity, it's actually more descriptive. It gives me more information. If you just said dne, that could be an oscillation, that could be a jump, it could be a lot of different things. Positive infinity looks like something very specific. It looks something like this. So now in the same manner, if x is going to 3, that's going to be negative infinity, right? It's because everything heads down more and more and more and more negative. What about at 7? What do you think is going on at 7? Okay, take a second and talk to the person next to you. What do you think is happening at 7? What's happening there? Okay, so first of all, let me ask, does the limit exist? Your answer should probably be no. Because even though it's approaching a number from the left side, it's not approaching a number from the right side. So there is no overall limit. So this is a discontinuity. What kind of discontinuity is this? It's an infinite discontinuity. Okay, so that's good. Can we say that the limit is infinity? No. And the reason is when we're talking about infinite limits, we're talking about coming from both sides. And this doesn't work on both sides, right? On the right side, it does great, but on the left side, it doesn't get bigger and bigger and bigger. So the other thing that we need to define here then, we can also talk about something being infinite or going to infinity or negative infinity from one side or the other. So one way that I can answer this, in general, I would have to write dne. But if I wanted to be a little more specific, if I come to 7 from the right side, the limit is positive infinity. If I come to 7 from the left side, the limit is whatever that number is. I don't know. If I make it up, it's like 2. Okay? So coming from one side versus the other, you can do that with infinite limits as well. Okay, so graphically, I mean, you've seen these types of things before, I think. So graphically, there shouldn't be anything too mysterious going on. It's just if we end up with some weird examples. Let me maybe give you one more weird example. I think in math, we tend to like weird examples. So I'm going to give you another kind of weird example here. We haven't seen this example before, although we've seen this example. Sine 1 over x. Do you remember what that one does? That goes like that, right? 1 over x sine 1 over x actually does something even worse. So it ends up looking, if you graphed it, I won't have you graph it now, but if you graphed it, it ends up doing this. Okay, which is even worse than sine 1 over x, okay? It does kind of the sine 1 over x behavior, but then it also has the 1 over x behavior that ends up getting bigger and bigger. So I want to ask, what is the limit as x goes to 0 of this function? Okay, obviously I would write d and e. Can I write positive equals positive infinity? No. And the reason is that if I make any cutoff, the function is getting bigger than this cutoff, but then it's turning and getting lower than the cutoff again. It's not eventually completely higher than that cutoff. So I could never say for this function, when x goes to 0, it's going to infinity or going to negative infinity. In fact, it's oscillating, and it's oscillating in a really super crazy way. Now, you could debate if you wanted to call this an infinite discontinuity or an oscillating discontinuity. It would kind of depend on your definitions. I would probably call it an oscillating discontinuity. So, okay, this is a weird example, but okay. So that's graphically, should make a fair amount of sense. Let's talk real briefly about numerically, doing these numerically. We're not going to spend a lot of time on how this works numerically, but I've kind of showed you a somewhat of an example before. So I'm going to take a different example. Let's take the limit as x goes to 2 of 3x over x minus 2 quantity squared. Okay, and I want to know, what is this doing as x goes to 2? What we would typically do for a numerical limit is we'd take the number 2 and we'd go out a little ways. So I'd start at 1.9, do 1.99, 1.999, kind of similar, 2.1, 2.01, 2.0001, and we're kind of wondering what's happening here. These are our x values. What's happening to the corresponding y values? Okay. Now, if you were to do this, I don't want to take a ton of time and just have you sit there and try to plug numbers in. But if you were to plug this in, what you would end up seeing is that these numbers are super big. That's a technical term, super big. Okay, when you do this, if you're setting up a table and you're plugging the numbers in correctly, sometimes you can plug them in incorrectly and this happens, but if you're plugging them in correctly and you end up seeing numbers, when you're getting close to the x value that you're looking for, you see these numbers are super huge, chances are you're looking at an infinite limit. So if I saw huge, big numbers here, like 1 million or something like that, then my guess would be that this limit is positive infinity. Okay, again, when you're doing numerical limits, it's always a guess. It's always a guess. You don't know for sure one way or the other. But for the most part, you can be fairly sure there. Okay, so numerical, again, come from both sides. If it's asking for that, if it's asking for one side or the other, you only come from one side. Plug in numbers close and see what the y values do. If the y values explode, positive or negative, then you're probably looking at an infinite limit. Okay? But nobody likes plugging numbers in, like, I don't know, I'm not a big numerical person. So how would we do this type of thing algebraically? And it turns out, in order to do it, doing it algebraically isn't actually that bad. Okay? So let's look. Let's see, what time is it? It's probably time to take a break. So let's take 5 minutes, give you a break, and we'll come back and we will finish up here and maybe even give you some time. It depends on how far we get. Okay, so pause this, take 5 minutes, and we will come back and finish up some thoughts about infinite limits. Okay, so let's talk about how do we do these limits algebraically. what are we looking for, and when that happens, what do we do? Okay? Let's take, for the most part, the situation that we're going to get is we're oftentimes going to be looking at a fraction. The top does not go to 0 and the bottom does. Okay, which is actually the previous example that I just did. So if I have the limit as x goes to 2 of 3x over x minus 2 squared, let's look at what happens here. So if I just try to plug in, the top goes to 6, and the bottom, if I plug into 2 minus 2 is 0, 0 squared is 0, so the top does not go to 0, it goes to some other value, and the bottom goes to 0. When this happens, it will be an infinite limit. Okay? It will be infinite because a non-zero number over a really small number is a really huge number. Okay? This will be an infinite limit. The issue that you have to figure out, is it going to positive infinity, or is it going to negative infinity, or is it maybe doing one on one side and one on the other? That's the part that you have to figure out. So if you see a fraction, the top's not going to 0 and the bottom is, it's either going to, both sides go to positive infinity, both sides go to negative infinity, or it's going to do one on one side and one on the other. So the way that you figure this out, when you know it's an infinite limit, you now have to look at the limit from the left and from the right and see what happens, okay? What you're looking for here in particular, because all we care about is it going to, we know it's going to infinity. Is it going to positive infinity or is it going to negative infinity? All that we really care about is it positive, or is the fraction positive, or is it negative? Let me explain what I mean by that. So if you look at this example here, when x goes to 2, 3x is going to 6. X minus 2 is going to 0. When I square it, it's going to 0. So the top is going to 6, the bottom is going to 0, so I know it's infinite. But I'll also notice something else. So if the limit is approaching 6, well, 6 is a positive number. So the top is actually a positive number as we're coming in to 2. The bottom's going to 0, but I need to know, is this going to 0 as a negative number getting close to 0 or a positive number getting close to 0? What you'll notice is that down here, the bottom is something squared. Well, something squared can't ever be negative. So the bottom here is actually always positive. So what I have here is a positive over a positive. I have a positive number that's exploding. That means that this limit has to be positive infinity. Does that make sense? So again, the top is going to 6, which is a positive number. The bottom's going to 0, but it's going to 0 as a positive number. It's something squared. Therefore, positive over positive gives me a positive number that's exploding, because I have 6 over a really small number is a really big number. That means this goes to positive infinity. Make sense? Let's look at another example. Let's get rid of the squared there and see what happens instead. Okay, so I'm going to look at the limit as x goes to 2 of 3x over x minus 2. Okay, here's how I would do this algebraically. I'd try to plug in first, and the top's going to 6. The bottom's going to 0, so I know that it's infinite. I've got that in the back of my mind. And I need to know, is this going to positive infinity or is it going to negative infinity? Well, I know the top is positive, but I don't know about the bottom because it depends on what side I'm coming from. Am I plugging in a number that's bigger than 2, or am I plugging in a number that's less than 2? And that's where I'm going to look at two different limits. When you don't have clarity there, what we're going to do is we're going to look at two different limits. First, we're going to come to 2 from the right side. Okay? The top is going to 6 again, that's positive. When x is going to 2 from the right side, think of a number to the right of 2, like 3. if I plug that in here, that number is going to be 3 minus 2. This is a positive number that's going to 0. So in this case, I have a positive number over a positive number. Any number to the right of 2 is still going to make this positive. So positive over positive means I'm going to have a limit that is actually approaching positive infinity. Okay, what happens if I come from the left side? Okay, if I come from the left side, then the top is going to 6, which is, again, positive. If I'm coming from the left side of 2, think of 2 and a number to the left. Number to the left of 2 might be like 1. If you plug in 1 here, this number is actually negative, and it's always negative if you're plugging in numbers that are less than 2, like 1.9. 1.9 minus 2 is still a negative number. It's going to 0, but it's going to 0 as a negative number. So all of this fraction is constantly a positive number over a negative number if we're to the left of 2. That means that this is blowing up, but it's a negative number that's blowing up, so the limit from the left side is actually going to be negative infinity. So visually, as x approaches 2, from the right side it's blowing up to positive infinity, and from the left side it's blowing down to negative infinity. So that's kind of what that function looks like close to 2. Does that make sense? So again, when you get, I'll do a couple more examples, but when you get a fraction where the top doesn't go to 0 and the bottom does, you know it's infinite. To figure out if it's positive or negative infinity, you have to look at what's happening on each side so you get clarity as to whether it's overall a positive number or overall a negative number. Okay? Let's try another example. I'll leave this up here because we want. Sorry, if I had more board space, I wouldn't have to keep erasing like this. Okay, let's take the example of limit as x goes to negative 1 of x minus 4 over x plus 1. Okay. Limit as x goes to negative 1 of x minus 4 over x plus 1. So what we're going to do here is first we're going to try to plug in when x goes to negative 1, the top goes to negative 5. Negative 1 minus 4 is negative 5. And the bottom goes to negative 1 plus 1, the bottom goes to 0. So immediately, just algebraically, immediately I know this limit is going to be infinite. But in order to figure out if it's doing this, or this, or this, or this, I have to look at what's going on from each side. So let's go from the right side first. So in other words, I'm plugging in a number bigger than negative 1. So the top again is heading toward negative 5. So overall, in terms of sign, the top is a negative number. The bottom, if I plug in a number, you got to think visually. Here's negative 1. If I plug in a number to the right of negative 1, like 0, this thing, even though it's going to 0, it's going to 0 as a positive number. Like if you plugged in 0, you would get a positive number here. If you plugged in 0.9, or negative 0.9, this is still a positive number. Any of those numbers to the right of negative 1 are going to give you positive numbers. So negative over positive means overall, this limit is negative infinity. So when I come to negative 1, from the right side, it's going down to negative infinity. Make sense? Everybody agree? Okay. When I go to negative 1 from the left side, again, the top's going to -5, so that's negative. Bottom's going to 0, but I want to know, is that a positive number or a negative number? If we take something to the left of -1, like -2, and plug it in here, that bottom number is actually going to be negative. So negative over negative, overall, this limit is actually going to be a positive number, so that's going to go to positive infinity. So if I come from the left side, I'm going up to positive infinity. So overall, this limit does not exist because the two sides don't match. But on the right side, it's going down to negative infinity, and on the left side, it's going up to positive infinity. Make sense? Okay. All right. So I think the last thing I want to do is introduce a definition that you've seen before, but maybe not had a formal definition for it. And it's the idea of the definition of a vertical asymptote, okay? So we've used this terminology before, a vertical asymptote. But because we have never talked about infinite limits before, you haven't ever technically seen them in other classes, we've never had a formal definition that we could make of this. So now we do. So we're going to say F has a vertical asymptote. Let me spell it out. So vertical asymptote. Watch the spelling on this. ASYMPTOTE. Asymptote. You don't actually say the P, so this is another case where the P is silent. Asymptote. F has a vertical asymptote at the number x equals a if any of the following 6 things happens. So if when you approach a, the function goes to positive infinity or negative infinity, or when you come from one side, like the right side, it's going to positive or negative infinity. Or when you come from the left side, it's either positive or negative infinity. Okay? So if any of these 6 things happens, so if you get overall limits positive infinity, overall limits negative infinity, from the right side it's positive infinity, from the right side it's negative infinity, or from the left side it's positive infinity, or the left side it's negative infinity, you're going to get a vertical asymptote. So as an example, remember that example that I did where I had at 7, you had something like this, and then, okay, that is this is a vertical asymptote here at x equals 7. And it's because the limit from the right side is positive infinity. It doesn't matter what's happening on the left side. If one of the sides has an infinite limit, then you get a vertical asymptote. Again, asymptote, ASYMPTOTE. Okay? So the kind of questions that you may get involving asymptotes would be something like the following. Yeah. Sorry, erasing again. Okay. Suppose I give you the function x squared plus 1 over x squared minus 1. And I ask, does f have vertical asymptotes? And if so, where and why? Okay. So we're looking for, what I'm really asking you to do is I'm looking for places where the function goes to negative infinity or positive infinity from one side or the other. Okay? So the first thing I want to ask is, given this function, where do you think would be good places to look for this function to go to positive infinity or negative infinity? Where would be good candidates? We know that this function's continuous because it's a polynomial over a polynomial, except in places where the domain, the numbers that are not in the domain. So that means places where, in this case, if x, the markers are getting tired here. Oops. Sorry. Yeah, that marker's kind of tired too. Come on, keep going. All right, when x is plus or minus 1, that's a place, those are the two places that are not in the domain, right? So this is continuous. Notice the function, you don't have to note this in what I'm to answer this question, but it's continuous on the interval from negative infinity to negative 1, negative 1 to 1, and 1 to infinity. Okay? Because it's a polynomial over a polynomial in the domain. It's continuous in its domain. Okay? At negative 1 and 1, what's going on? The way that we're going to tell is we need to take a limit. So I want to know what's the limit as x goes to 1, and what's the limit as x goes to negative 1. I want to examine that, and then based on what the answer is, that's going to tell me that's going to tell me what's going on here. So if I start with 1, what's happening at 1? The first thing I do is try to plug in. So this is going, the top's going to 2, and the bottom's going to 0. And what does that immediately tell you? That this is going to be an infinite limit. Okay, which technically does mean that you're going to have a vertical asymptote at 1. We need to gather a little more information, but technically we know now that we're going to get a vertical asymptote here. And the way that we figure out what's going on is we look at the two separate limits. So we're going to look at the limit from the right and then the limit from the left and see what's happening here. Okay, when we look at the limit from the right, okay, when x is going to 1 from the right, the top's going to 2, so again, that's positive. Let's pick a number to the right of 1, like 2, and plug it into the bottom. Like if I picked 2 and plugged it in, I would get 4 minus 1 is 3. That is a positive number. And positive over positive means that when I come to 1 from the right side, the function's going to positive infinity. So if I was graphing the function, and here's 1, when I come to 1 from the right side, the function's going up to positive infinity. Okay? Now let's take it from coming from the left side. So if I come to 1 from the left side, the top is still going to 2, so that's positive. But if I'm coming to 1 from the left side, like pick a number to the left of 1, like 0, I'm going to get 0 minus 1 is negative 1, so the bottom is going to be negative, and overall, the left side goes down to negative infinity when I come to 1 from the left side. So at 1, we definitely have a vertical asymptote at the line x equals 1. Okay, what's happening here for x going to negative 1? Let's look at each side this way too. So if I plug in, let's plug in. The top goes to 2 and the bottom goes to 0. So we're in a similar situation. We know that this is going to be an infinite limit 2. And if we come from the right side of negative 1, the top is going to 2, that's positive. The bottom's going to 0. If I pick something to the right of negative 1, like 0, 0 minus 1 is going to be negative, so overall this limit is negative infinity. So if I come to -1 from the right side, the result is it's going down to negative infinity. Make sense? If I come to -1 from the left side, again, the top's going to 2, which is positive. Bottom's going to 0. If I pick something to the left of -1, like -2, and plug it in, -2 squared is 4, -1 is 3, that's positive. So overall, when I come to -1 from the left side, this is going up to positive infinity. So this is actually, so you get a vertical asymptote at x equals -1 and at x equals 1, but we actually kind of know what the, at least in part, what the graph of this function looks like based on these limits that we calculated. It's pretty nice, right? Well, you could think of it as nice. I don't know. Okay. All right. Let's take a look at one more example, and then I think we're done for today. So okay, same concept. I'm going to give you a function and say, where are the vertical asymptotes? Okay. So I've got a function x squared plus 2x minus 8 over x squared minus 4, and I'm asking, where are the vertical asymptotes? Okay. So again, let's think through where are the candidates for vertical asymptotes. This is a polynomial or a polynomial. So it's going to be continuous everywhere except where the bottom equals 0 and the bottom equals 0 where? At 2 and -2, plus or minus 2. So we have to look at what's going on at 2 and at -2. So we're going to look, to figure out what's happening, we're going to look at what's going on at 2. If we try to take a limit there, and then at -2. Okay, so let's start with what's happening at 2. If we plug in, I get 4 plus 4 minus 8, so the top goes to 0. And then 4 minus 4, the bottom also goes to 0. So this tells me I'm in this scenario over here. And I should probably do what? Yeah, I should probably factor and cancel. So I'm going to factor the top. And I think I gave you the trick that if the top goes to 0, there's actually a factor here of x minus whatever this number is, so x minus 2. The other part turns out to be x plus 4. And the bottom factors is x minus 2, x plus 2. So because I'm not right at 2, I can cancel these and let x go to 2, and the top is going to go to 6, and the bottom is going to go to 4. So the limit is actually 3 halves. What does that tell me? If I was graphing this, at 2, the limit is 3 halves. I don't know exactly what that looks like, but it's probably, it's not defined at 2, but it's probably going to look something like that. Is that a vertical asymptote? No, that is not a vertical asymptote. That's not becoming infinite. So we do not have a vertical asymptote at x equals 2. That is not a vertical asymptote. So just because the bottom goes to 0 doesn't mean you have a vertical asymptote. If the top goes to 0, you've got to do some checking first. Make sense? But on this side, it turns out we are going to get a vertical asymptote. So when x goes to -2 here, we get 4. 2 times -2 is minus 4. So 4 minus 4 is 0 minus 8. So the top goes to -8. And the bottom goes to 0. And we automatically know that we're talking about an infinite limit here. And we need to look at what's happening from each side. Okay, so we kind of already know that we're going to have a vertical asymptote here. Let's look at what happens from each side. So if we come to -2 from the right side, okay, again, the top is going to -8. So the top is negative. If I pick something to the right of -2, think visually. So something like -1. If I plug in -1, -1 squared is 1 minus 4. That gives me a negative number. So overall, what kind of infinite limit is this? This is a negative over negative is going to give me positive infinity. So as x comes to -2 from the right, this is going to go up to positive infinity. And if you were to check this, x goes to -2 from the left. Okay, again, the top goes to -8, which is negative. And then the bottom goes to 0, but if I'm to the left of -2, like -3, if I plug that in, -3 squared is 9 minus 4 is actually a positive number, so overall this is negative over positive is negative infinity. So this is what that function ends up looking like, kind of generally. We have a vertical asymptote at x equals -2, because we have an infinite limit there, but we do not have one at x equals 2. Okay? Make sense? So we kind of added one more thing to our list here of how to do limits algebraically. If we have a function over a function, the top does not go to 0 and the bottom does, we know that this is going to be an infinite limit. And we just have to check from the left and from the right. We need to ask the question, is this positive or negative? Okay, if it's positive, it's going to go to positive infinity. If it's negative, it's going to go to negative infinity. Okay? All right, so next week, Monday, again, we'll finish up. I've just got a couple of last things that I want to say about infinite limits. We'll start to get a preview on derivatives. Wednesday, we have a shortened class period. It's in the morning. Then Thursday, we'll do review for the Chapter 1 exam on limits and continuity. And then the following week on that Monday, we'll have that exam. So you guys have an awesome weekend, and I will see you all later. Thanks.